Okay, get this. What if a factory could actually help stabilize our power grid? It sounds kind of backward, right? But today, we're looking at this incredible new technology that dusts off an old industrial process and completely reinvents it to solve one of the biggest headaches for renewable energy. So let's dive in and see exactly how they pull this off. It seems like a trick question, doesn't it? I mean, how can you possibly have too much of a good thing like wind or solar power? Well, it turns out this is a very real and actually a very expensive problem for our modern energy grids. And that brings us to what you could call the green energy paradox. It's this surprising and honestly pretty frustrating challenge that pops up when our renewable energy sources are, in a weird way, too good at their job. Yeah, the short and painful answer is all that extra power just gets thrown away. The official term for this is curtailment, and believe me, it's a massive source of inefficiency as we're trying to shift to clean energy. So here's the deal. On a really windy or super sunny day, renewables can totally flood the grid with way more electricity than we're all using. And since we don't really have giant batteries to store all of it yet, the grid operators have no choice. They literally have to call up wind farms and say, hey, shut down your turbines, or tell solar farms to unplug their panels. In a place like West Texas, this forced shutdown means billions of dollars worth of clean energy just vanishes. Poof, gone. But what if, instead of just wasting all that energy, we could grab it and redirect it to do something incredibly useful? This is exactly where the idea of a power sink comes into play. A power sink is basically a giant, energy-hungry industrial plant that's designed to be super flexible. It can fire up its operations specifically to soak up all that cheap, extra electricity, turning what was a grid liability into a really valuable physical product. And this schematic shows you the idea perfectly. Instead of telling the wind farm to shut down, you just flip a switch and you channel all that extra power directly into these massive industrial furnaces. You're putting that energy to work instead of throwing it away. Now, what's really amazing here is the sheer flexibility of this thing. This magnesium plant can just hum along at a base load of 23 megawatts. But when the grid is overflowing with power, boom, it can ramp all the way up to absorb a whopping 155 megawatts. That range is huge, which makes it the perfect dance partner for the kind of unpredictable nature of wind and solar. So how does it actually work? Let's step inside the plant, so to speak, and look at the first major step in the process, using all that electricity to create a superheated cloud of magnesium vapor. Okay, we're going to walk through the 4 key steps of this modernized process. It basically takes a method from the 1940s, the permanent process, and gives it a massive upgrade with modern tech. It all starts with a simple reaction and ends with pure, solid metal. All right, step 1. You take your raw materials, magnesium oxide, which is basically a white powder, and plain old carbon, and you feed them into a sealed electric arc furnace. This furnace uses all that surplus renewable energy to get incredibly hot. We're talking over 1,700 degrees Celsius. That's more than 3,000 degrees Fahrenheit. At that insane temperature, a reaction called carbothermal reduction kicks off. Essentially, the heat is so intense that the oxygen atom just lets go of the magnesium and grabs onto a carbon atom instead. And what you're left with are 2 gases, pure magnesium vapor and carbon monoxide. You've literally turned solid powders into a cloud of metal vapor. But this is where the real trick comes in. See, the problem is, this whole reaction is reversible. If you let that hot gas mixture cool down slowly, the magnesium and carbon monoxide will just find each other again and turn right back into the powder you started with. All that energy just wasted. So the key, the real magic here, isn't in the heating. It's all about the cooling. And that brings us right to the heart of the innovation. This is a totally new way to think about cooling that stops that back reaction dead in its tracks and makes this whole thing possible. I just love this quote from the patent because it perfectly captures how intense this is. Instead of some gentle cooling process, you inject a liquid coolant straight into the hot gas, and it explodes into vapor. This whole explosive phase change happens in a blink of an eye, instantly flash freezing the magnesium vapor into tiny, solid particles before it even knows what happened. And this comparison just shows the incredible leap in technology. The original 1940s process, over on the left, tried to cool the vapor by mixing it with a huge amount of methane gas. It was slow, it was inefficient. The modern process, on the right, uses a special liquid coolant. By harnessing the massive amount of energy a liquid sucks up when it boils, that's the heat of vaporization, it creates this incredibly rapid, almost instantaneous flash cool. So, what happens to everything after that flash cool? Well, first, the gas stream goes through these high temp ceramic filters that grab all these solid magnesium dust. Then, that dust gets melted down and cast into pure magnesium ingots. After that, the leftover gases, coolant vapor, and carbon monoxide are chilled down. And finally, the liquid coolant is recovered to be used again, leaving you with pure captured carbon monoxide gas, a very clean separation. So, we've gone through the chemistry and the engineering, but let's zoom back out for a second and talk about why this is so much more than just a clever factory. It's a potential game changer. I mean, we are not talking about some small-scale lab experiment here. A single one of these plants is designed to crank out 100,000 metric tons of magnesium a year. That is industrial scale production. It's turning a huge energy problem into a massive economic opportunity. So the key takeaway is really threefold. One, it helps stabilize the grid by soaking up that unpredictable renewable energy. Two, the economics are just brilliant. You're taking electricity that often costs nothing or is even negatively priced and turning it into a high-demand metal. And three, it's a big win for sustainability because that pure carbon monoxide you capture can be used to create next-generation synthetic e-fuels. And let's not forget about the final product itself. Magnesium is a bit of a wonder metal. It's incredibly lightweight, but also very strong, which makes it absolutely essential for everything from making cars and airplanes more fuel efficient to the sleek cases on our laptops and phones. This process could create a reliable domestic supply of a really critical modern material. And this whole idea really opens up a fascinating line of thinking, right? This tech can be tweaked for other metals like zinc or silicon. It really makes you wonder, as our grid relies more and more on these fluctuating renewables, what other classic, energy-guzzling industries could be totally reimagined as flexible power sinks, turning our biggest energy challenges into our next great innovations?